This video is to explain a bit more about non-convex regular polygons, like these shapes, as they'll be cropping up in videos about non-convex polyhedra, and not everyone will be familiar with them. If someone asked you to draw a regular pentagon, you'd probably come up with this shape. But this is also a valid regular pentagon. This is called a pentagram. It has equal side lengths and equal vertex angles, so it's regular. Similarly, a regular octagon is normally thought of as this. But this is also a regular octagon. 8 sides of equal length and equal angles. A regular heptagon has 3 variants: this, this, and this, and so on. You can create a non-convex polygon by plotting the vertices of a convex polygon, then connecting them, missing out a vertex each time. So a pentagram is a pentagon's vertices, joining every second vertex. A pentagram is also called a 5/2gon. With 7 vertices, joining every second vertex, we get a 7/2gon. Joining every third vertex is a 7/3gon. A 20/7gon is 20 dots with every 7th vertex joined. The second number in these names has an important meaning. If you move all the way around the sides of an 8/3gon, for example, you'll find you've circled the centre 3 times. So the 3 in 8/3gon indicates the number of times the centre is encircled, known as the density. Strictly speaking, only the centre part is surrounded 3 times. These parts are surrounded twice, and these parts once. The density concept can be stretched further. You can create a 7/4gon, which is like a 7/3gon, but the sides encircle the vertex in the opposite direction. These two are usually considered the same, but sometimes the direction of encirclement is used to assign a front and back. So a 7/4gon is, in a sense, a reversed or inward-facing 7/3gon. A 7/1gon is just an ordinary convex heptagon, while a 7/6gon is a reversed convex heptagon. The number of sides cannot be a multiple of the density. For example, an 8/2gon is just 2 squares. It also fails if the number of sides and the density have a common divisor. 10 and 4 are both multiples of 2, so a 10/4gon is just 2 5/2gons. There's a reason why these numbers are written as fractions. Going back to the pentagram, it has 5 sides and density 2, so it's a 5/2gon. Now 5 divided by 2 is 2.5, and in many ways the 5/2gon behaves like a polygon with 2.5 sides. In fact, most formulas for properties of convex regular polygons hold true for the pentagram if we treat it as having 2.5 sides. I won't linger on the mathematics here, you can pause the video if you're interested, but all these formulas for convex polygons give the correct answers for any concave polygon if you set n equal to the number of sides divided by the density. When calculating the area of these shapes, the higher density parts are counted multiple times, so the area of the octagram is 3 times the orange area, plus 2 times the bright yellow area, plus the dull yellow area. This might seem overcomplicated, but it's actually simpler to calculate in practice. An intriguing alternative way to create a non-convex polygon is to start with a convex polygon and move the sides inwards. For example, starting with a 9-sided polygon, we can derive a 9/2gon, then a 9/3gon, which is actually just 3 triangles, then a 9/4gon. Continuing, we then get a 9/5gon, which is a reversed 9/4gon, then on through 9/6gon, 9/7gon, and finally 9/8 gon, the reverse of the original. Finally, there's no limit to the number of sides or density. You can have a 97/28 gon if you want, but the shapes we'll encounter in the upcoming videos are mostly the pentagram, the octagram, and the decagram. I hope this was interesting. See you in the next video.